Hello, everybody, and welcome to UC Observatory's weekly virtual event series. We're going to get started now. You'll have to bear with me because I'm still admitting people in as they're coming onto the stream. So my name is Marianne Campbell, and I am the Communications Specialist for UC Observatories. Dr. Alex Filippenko joins us today. He is, as you're probably aware, he has a large body of work. His scientific accomplishments have been documented in near countless research papers, and he's one of the world's most highly cited astronomers. We're delighted that he can join us today. We've received a record number of questions for Alex, and he has selected the ones that he's going to answer today, and we will do our best to get through them in the next hour. We really hope that you find this session illuminating and that you learn something from today's session. So I'm going to turn it over to Alex to say hello, and then we'll get started with the first question.
Well, thank you very much, Marianne, for organizing this. And I'm delighted to see 113 participants and growing. Wow, what a group. As Marianne said, we received really a lot of questions. In fact, so many that I'll try to hold another one of these Ask-an-Astronomer sessions later on this summer, maybe in August. Thank you so much for your interest in astronomy and in the University of California Observatories. UC is proud to be a partner in the WM Keck Observatory, and I have a t-shirt on here advertising that. And we own and operate the Lick Observatory, which is in my background here, which is just a short drive from Silicon Valley, but it's closed to the general public right now, unfortunately, because of the coronavirus. And we hope to build a 30-meter telescope as well, probably in the Canary Islands, maybe Hawaii. And we have various instrument labs where we build spectrographs and imaging devices and all kinds of things like that. So thank you for your interest, and I'll try to get through as many questions as possible. In the interest of time, my answers will be brief, and some of the questions that are more involved I'll probably reserve for next time or something like that. But anyway, delighted that you could join me here. Marianne, why don't you go ahead and read the first question to me?
Okay, so our first question comes from Jim Grubb, and he sent us that via our social@ucolick.org email. And he asks, what is the most interesting thing that we have learned or discovered from the APF at Lick?
Yes, the APF is the most recent telescope at Lick Observatory. It's the automated planet finder. It takes spectra of stars, that is, it breaks up the light into its component colors every night of the year, basically, when it's working, when it's not cloudy. And it looks at the same stars over and over and over again, and it tries to measure the speeds with which those stars are moving toward us or away from us. And if a star is in a circular or an elliptical orbit, if there's a planet with a circular or an elliptical orbit around the star, then the star moves a little bit as well, because although we say that planets go around stars, really they orbit their common center of mass. So as the planet moves, the star moves a little tiny bit as well. It's sort of like a person walking or a person running. Those are the kinds of motions that we can detect. And the advantage of having the APF, which was finished in 2013, is that we can look at the same stars night after night after night, even several times the same night if we want to. And that kind of repeated observation is difficult to do at other observatories where there's much less time to look at the same stars every night. Now, it's hard to say what the single most important or interesting discovery has been. A lot of the data are still being processed, but I'll mention a couple of discoveries that I think are really cool. One is that there's a planet going around the star HR 5183. That's its phone number. So planet HR 5183b sort of slingshots its way around the star, a very highly elliptical orbit. It's very eccentric. The eccentricity is 0.85, which means it's, like a cigar. And it has an 80-year-long orbit. So that's one of the longest known orbital periods for an exoplanet, a planet orbiting another star. At least one of the longest such periods for planets discovered using the radial velocity method. There are some planets that are imaged, and they're quite far away from the star that they orbit, and so they have long orbital periods. But using the radial velocity technique, this is one of the longest orbital periods ever found. And with the nightly cadence of the APF, they were able to monitor the very rapid swinging around of the planet going around the star when it's closest. It was kind of like, it was like a wrecking ball. That was the description, because it was changing very quickly. It was a little bit like a comet getting close to the sun, like Comet Neowise, or about which I know there are some questions later. It zips around the sun. In a similar way, when a planet zips around a star, the star moves most quickly, and that nightly motion was needed from the APF in order to monitor this. So that was really cool. 80-year-long period. And then the other interesting thing is that there's a star called HD 219134. And it has two rocky Earth-like planets that were originally detected using this Doppler radial velocity method. But the orbital plane is nearly along our line of sight. And so those two planets also pass between us and the star, causing transits. So they block a little bit of the star's light. And that amount of light can be measured, the amount that's blocked. And that gives the size of the planet relative to the size of the star. And knowing the size of the star, you can then figure out the volume of the planet. And knowing the mass of the planet, which you get from the Doppler radial velocity technique, and knowing the volume, you can get the density. And so we can tell that these are dense, rocky, Earth-like planets with a metallic core. So that's really, kind of neat. And then this isn't really a discovery, but I thought I'd mention that APF is also involved in the Breakthrough Listen project, where there's like, $100 million being placed into this search for signals from extraterrestrial aliens. And the APF data are useful because you can look in the spectra potentially for very narrow wavelength laser lines that might be emitted by some extraterrestrial civilization. And those data are actually open to the public. Anyone can look for laser lines. You can probably find it by Googling or using your favorite search engine to type in, automated planet finder, Lick Observatory, laser lines, or something like that. So no discovery yet, but we're looking for ET. Okay, Marianne, I think we can go to the next question.
Okay, so the next question is from Richard Hubbard, and this is again via social at UCO-LIC. How did astronomers discover brown dwarf stars, and how long have they known about them?
Yes, brown dwarfs. So those are stars that are not quite massive enough to fuse the normal form of hydrogen, which is just a single proton, together with another proton in a chain reaction that then gives you helium. Brown dwarfs aren't quite massive enough and hot enough and pressurized enough inside for that fusion reaction to occur. However, they can fuse a heavier form of hydrogen called deuterium. So they do fuse for a while. It's just that there's not much deuterium compared to normal hydrogen. So they fuse for a short time. That makes them not quite planets. They're more massive than planets. Planets never fuse at all. So they're sort of in the mass range between the most massive planets, 10 Jupiter masses or so, and the least massive normal stars, about 75 Jupiter masses. And they do fuse deuterons. So they were predicted in the 1970s, 80s. And then in the early 1990s, they were first found. And the first ones that were found orbiting nearby stars. So people took images of those stars, especially at infrared wavelengths, because brown dwarfs, being so low mass, are very cool. And so they emit more in the infrared than the optical. So a few little dim companions were found to some nearby stars. Too bright to be planets, but too dim to be normal stars. And then with the development of infrared arrays, sort of like CMOS devices that are used, you know, in your cameras, or charge coupled devices that astronomers use. In the infrared, the technology in the early 1990s became such that you could make arrays with, you know, hundreds or even thousands or even 10,000 pixels. And then with those arrays, we could take images of the sky at infrared wavelengths. And when you point to regions of star formation, like the Orion Nebula, lots and lots of faint little guys were found that were too faint to be stars, but too bright to be planets. And now, you know, literally thousands of these brown dwarfs are known. But I'd say early to mid 1990s when they first started being found, coincidentally perhaps, or maybe because of the improvement in technology, that's right around the time that the first exoplanets were being found. By the way, at Lick Observatory were among the first ones. 70 of the first 100 were found with the Lick 3-meter Shane reflector. And that's also around the time that the first trans-Neptunian objects, you know, these things beyond Neptune and Pluto, the Kuiper belt objects, they started being found in the early to mid 1990s. And really, I would say it's in the improvement of CCD optical arrays and infrared arrays that help to find, you know, brown dwarfs and these Kuiper belt objects and trans-Neptunian objects. And then it was different technology, the radial velocity technique at around the same time, mid 1990s, that led to the detection of exoplanets.
Okay.
Okay, I think we can go to the next one.
Okay, so our next question comes via Instagram, and this one's from Michelle Profant. I hope I said that right.
Okay.
And her question is about primordial black holes and dark energy. So she says, if dark matter is primordial black holes, could Hawking radiation be dark energy?
Oh, interesting hypothesis. So, you know, you can spend hours talking about both primordial black holes and Hawking radiation. Actually, only a few minutes about bright primordial black holes because nothing is known about them. It's just theorized by some theorists that black holes might have formed very early in the history of the universe as a result of density fluctuations in the early universe. You know, just because of random things, sometimes you get more dense regions and sometimes less dense regions. And if you have a really big uptick in density, it could collapse to form a black hole. That would be a primordial black hole. We don't know of their existence, but they might exist. And then Hawking in 1974, the thing for which he's most famous, did the first steps in sort of combining general relativity, Einstein's theory of gravity, with quantum physics, the theory of, you know, atoms and molecules and subatomic particles and things like that. We don't have a fully verified or fully well-developed quantum theory of gravity yet, but it's thought that any generic quantum gravity theory will have this feature that Hawking theorized about, and that is that when you combine quantum physics with general relativity, you predict that black holes aren't completely black. Although gravity is so strong that nothing, not even light, can get out, that's a classical description. If you bring in the quantum world, then particles and antiparticles can escape. And that's what's known as Hawking radiation. So, and by the way, that hasn't been found. It's just theoretical right now, but we think it does exist. So if black holes that are primordial exist, then Hawking radiation from them could be quite strong at this point, because some of those black holes are low mass black holes, and the low mass black holes have stronger Hawking radiation than big black holes for reasons I won't go into right now. But anyway, those primordial black holes could be evaporating at a ferocious rate right now. And the question then is, from Michelle, could this be, you know, dark energy? Good try, but doesn't work that way. Hawking radiation is the type of radiation that has a positive attractive gravity, whereas dark energy, which is causing our expansion of the universe to accelerate with time, is not a negative energy, but an energy with a negative pressure. And Hawking radiation doesn't have that property. So dark energy, if it exists, is almost certainly not Hawking radiation, but good try, very creative of you. Okay, Marianne, next question.
Okay, so this question is from Ian Clements, and this is also via Instagram. He asks, what if black holes aren't holes at all? Instead, what if things that seem to disappear were warped? Would that fit the physics better or worse?
Yeah, so, you know, the evidence for black holes is both theoretical. Einstein's general theory of relativity predicts that such objects could exist, even though, interestingly, Einstein resisted that prediction for most of his life. And then the observational evidence is not that we see things, you know, disappearing randomly in various places. It's that we see objects in orbit very quickly around regions that don't seem to be glowing. And yet, from the orbital speeds and periods, you can figure out that the object around which the thing we do see is orbiting, it must be very massive. And if it were a star that's very massive, it would emit light. And other, you know, things can be ruled out as well. And, you know, they would all be visible, but they're not visible. And so we conclude that it's a black hole. So it's not that we actually see things being sucked in and disappearing. So first of all, we don't find things that are just disappearing. And second of all, both theoretically and observationally, the physics of black holes is by far the most reasonable explanation for the observations we have. And then the closest thing we have to a picture of a black hole is this thing that the Event Horizon Telescope team published a year ago in April, where looking at the center of the galaxy M87, they see a disk of glowing gas around a reasonably dark hole. So it looks like a donut. And that's really the shadow or the silhouette of a black hole. It's the region from which light doesn't come, but we can see the stuff glowing around it. And the size of the silhouette is exactly consistent with the size that was predicted based on the orbital motions of stars in the center of that galaxy. So the evidence is very good. There's also evidence for black holes from gravitational waves. And so most of us are pretty darn convinced that black holes really do exist and that they are the best physical explanation for the data. Okay.
Okay.
Very good.
So the next question
Go ahead,
comes
Marianne.
via Facebook, and I hope I pronounced this correctly. It's from Ivailo Vartigorov. That was my best attempt. Can we predict a gamma ray burst in time? Is there a way to protect ourselves in future, or are we 100% doomed if it is directed towards the Earth?
One of the doomsday scenarios, yeah. So a gamma ray burst is, you know, a big burst of gamma rays, the highest energy known for radiation, electromagnetic radiation, but there's also all kinds of other stuff as well, X-rays and ultraviolet visible light. We've detected gamma ray bursts throughout the electromagnetic spectrum. And the point is they're sort of beamed. They're like water coming out of a hose or a hydrant, you know. And if they're beamed at us, then we get this onslaught of radiation. They're not that dangerous if viewed from the side. But if they're beamed at us, then they're very dangerous indeed, because their radiation goes out for thousands of light years throughout a galaxy and basically sterilizes planets along the line of sight. That's pretty bad news. And although we know now roughly what kinds of stars might explode in that way, we don't know very well whether they're pointing at us and how precisely they're pointing at us. There's a few stars, WR104 is one of them, if memory serves me correctly, that's sort of pointing at us. But, you know, I think it's like 15 or 20 degrees off, and that's good enough to be safe. You need to know pretty precisely that it's pointing at you. And we don't know of any such stars. If we did know of such a star, even if we had, 100 years to prepare, I'm not sure what we'd do about it, because what happens is the gamma rays come in and they destroy most of the ozone layer. or at least half of it. And then that would let in the long run, a lot more ultraviolet light from the sun. And so then the little bacteria and microbes and the, the plankton and stuff in the oceans die, especially in the surface layers, because the gamma ray, the ultraviolet light doesn't really penetrate that far into the oceans. But near the surface, the life dies, and that then destroys the, the big food chain, right? The bigger guys eat the little guys, and then even bigger guys eat those. So I don't know what we do with our food chain. Even if you could hide in a bunker, somewhere in the Rocky Mountains, like some of the bunkers that you hear about that have been built for politicians or whatever, the military, in case of some giant war, our atmosphere would be messed up for hundreds of years, if not thousands. I'm not an atmospheric scientist, so I'm not sure how long it would take the ozone layer to replenish itself. Also, various nitrics and nitrous oxides form, and then they come down as acid rain and stuff. So life wouldn't be very pleasant here on Earth for years, if not decades or even a century. I haven't, I'm not an engineer or also one of these people who spends their time figuring out how humanity is going to survive under various doomsday scenarios. But that's a pretty bad one. Not because we get killed instantly, but I think mostly because the whole food chain is destroyed. And I'm not sure what to do about it. Okay. Why don't we move on to a happier topic?
Hopefully that's a very unlikely scenario. So
yeah, it's pretty. Look. Yeah, thank you, Marianne, for bringing me back to reality. There are many things to worry about, much more. Climate change, and obviously for the short term, all of you stay safe, wear your masks, physically distance. Believe the medical experts. And then, of course, there's climate change. And then if you look at things like asteroid impacts are a much greater danger, or even coronal mass ejections from the sun. They won't destroy all of humanity, but if our grid goes down for 9 months or 12 months or something, there's not a lot of spare transformers sitting around. And you can imagine what would happen if, even globally now, not let alone locally, if all of our energy sources suddenly went away, if the whole power grid went down. So that's one reason solar astronomers are monitoring the sun with satellites 24/7, so we can tell the power companies when to shut down the grid, because we can at least prevent the short circuits of the transformers that occur when currents go along big long wires. Those are the worst kinds of short circuits. We won't be able to protect the transformers against little short circuits with inside them, but from my understanding, the biggest currents are along the long wires that go from one power station to another. And those we can prevent that. That's a preventable disaster. And the big asteroid coming in, we're searching for those too. So for the 10-kilometer sized ones, the mass extinction kind, we can find those, at least most of them, well before they hit. And then clever applied physicists and engineers can figure out a way to deflect them. So support your local astronomer. He or she may someday help save humanity. All right, let's go to the next question.
Okay, this one is from Bruce Anberg via social at UCLEC. And he says, as a member of the stargazing public, would you take a moment to comment on the amazing alignment these past few days in the southern sky before dawn of Mars, the waning moon, Saturn, and Jupiter? I can't remember seeing this before in my life, with both Saturn and Jupiter in opposition this month and Mars nearing it. This must be something special and won't be repeated until who knows when. Is this the kind of thing that turns young people into future astronomers?
Oh, it's a beautiful sight. Great question. Yeah, bring us back to the wonders of looking at the sky. Yeah, for all of you, it's go out, even 10, 11 p.m. now, Jupiter and Saturn are up pretty early, near opposition, in fact, which means they're high in the sky around midnight, or I guess 1 a.m. since we're all in daylight saving time, unless you're in Arizona or something. But Mars and Jupiter are very easy to see. Mars is the really bright thing in the south. Saturn is just a little bit to its left, to its east, a little bit fainter, actually significantly fainter, but they're quite close together in the sky. And Mars and Jupiter are close together in the sky for a while, a number of months. roughly every 20 years. And that's because Jupiter has an orbital period of 12 years around the sun, and Saturn around 30, 29 and a half, something like that. So if you figure things out, just draw little circles around the sun and have these different periods, 12 years and roughly 30 years, you'll figure out, it's not that hard actually to do, that roughly every 20 years or so, they're close to each other for several months, for the better part of a year. And so the last time was in the year 2000, and the next one will be 2040. That's not super rare. Now, Mars being close to them, it's actually significantly away by now, but you're right, a couple of months ago it was pretty close. Yeah, so all three of them that close, that's of course rarer. I'd have to figure that out. I actually haven't done that calculation. And then, once you've got those three, the waning moon will be among them, well, once a month, or some moon will be among them. It won't necessarily be waning. But yeah, the more planets and stuff you add, the greater is the length of time between appearances of that sort. So it's quite special. It's very pretty. They're very bright. But when I was a kid, there was this book called The Jupiter Effect. And there were these people who were just trying to make a lot of money. And they said that, in 1984, not only Jupiter and Saturn, but a bunch of the planets will line up, and that'll cause all kinds of earthquakes on Earth and stuff. And they were probably selling potions that you could buy that would prevent you from being hurt. They either believed it themselves, or more likely they were trying to capitalize on a very, very gullible public. But of course, nothing happened, and astronomers predicted that way in advance, that the tidal effects of Mars and Jupiter and Saturn lining up are negligible compared to what the moon does, or especially when the moon and the sun line up, like at new moon and full moon. Those are all much bigger effects, and nothing much happens, okay? So this has happened before. 1984 came and went. But for Jupiter and Mars, yeah, I think closest approach is something like in December, but they won't be as easily visible all night long in December. So these summer months, go out and take a look. And if you have young kids or friends of kids, take them outside, because this can be a way to inspire youngsters. Thanks for that question.
Okay.
We can go on to the next one.
So this next one comes from our email, and this is from Isaac, but I think he goes by the name of Cappy, because that's what he's put in brackets here. And he says, what is the mechanism that binds stars together in clusters like M13?
Oh yeah, so M13 is a globular star cluster, one of around 150 or 200 that are known going around our galaxy. They consist of, something like 500,000 to 1 million stars each. And what's neat about them is that they're the oldest discrete structures whose ages we've measured with some accuracy in our galaxy. They're 12 or 13 billion years old. And our galaxy is only about that old. So they're among the oldest structures in our galaxy. And, our universe is only about 13 or 14 billion years old. So they're really very ancient. Gravity binds them together. You've got 500,000 to 1 million stars. Each of them is pulling on each of the others. And so since they're all pretty close together, gravity binds them. Occasionally, they go zipping past each other. And especially when there are 3 stars that go zipping past each other just because of random motions, one of them might gain an extra amount of energy and be flung out of the globular cluster system. So these globular clusters are very gradually evaporating. If you think of individual stars like molecules from an evaporating glass of water. But gravity holds most of them in. Okay, great.
Okay. Our next question came via email, and this is from Marty Schwartz. And the question is, please explain the 3 principal methods for measuring the expansion rate of the universe, and why the rate determined by these methods is different than the rate determined by the cosmic microwave background measurements.
Wow, Marty, great question. The subject of hundreds of research papers. Bottom line, we don't know the answer why today's measurement, with which I'm involved, by the way, roughly 75 kilometers per second per million parsecs, which is about 3.25 million light years. Don't worry about the units if you don't know, for the general people listening, versus 68 or so kilometers per second per megaparsec. measured by the cosmic microwave background experiments, most recently the Planck satellite. So that difference is now, we think, statistically significant at the 5 standard deviation level. We're measuring a faster rate than the one predicted from measurements of the early universe and extrapolated up to now. So maybe someone gave the early universe an extra kick. So the analogy I like to give is that you're watching some kid's soccer game and you see a soccer ball go zipping by much faster than, or significantly faster than any single kid can kick it. So you think, well, maybe another kid kicked it before the most recent one, you know. So there was 2 kids kicking it, not 1. So your assumption was wrong. So maybe it's something like that, or maybe dark energy is getting stronger or something like that. We're really not sure what the discrepancy is caused by. But the 3 main measurements that are made for the Hubble constant, this rate of expansion now, and let me try to be brief, are the following. The one with which I'm most involved is the use of what are called type 1a supernovae. These are dense stars called white dwarfs that are in a binary orbit with another star, and they gain enough matter to become unstable and they explode. And you can measure how bright they are in galaxies of known distance, and then you measure how bright they appear to be in galaxies that are farther away. And then, just like you can compare the brightness of the headlights of a car at known distance nearby and the dim ones far away, your brain is using the inverse square law of light, and it determines the distance of the more distant car. The nearby supernovae in galaxies that are used as calibrators, we know their distance because those galaxies have Cepheid variable stars in them. And Cepheid variables are a very well recognized form of a star. We know their true power. They're like the car that's nearby. And we know that going back to Henrietta Leavitt's work at Harvard in 1912. She found them in the Large Magellanic Cloud and the Small Magellanic Cloud, 2 satellite galaxies of our Milky Way. And we've now measured the distances of the clouds very well. And so we know the power of these Cepheid variables. And you might think, if they're variable, how do we know their power? Well, they're not all the same, but the ones that are intrinsically more powerful brighten and fade on a longer time scale than the ones that are less powerful. So there's a period luminosity relationship. You can see it gets complicated. But anyway, we've measured the period luminosity relationship. We know the distance to the clouds. We thus know the luminosity of the Cepheid variables. We then find them in nearby galaxies in which we've also found type 1a supernovae. That calibrates the type 1a's. We then find type 1a's in the more distant galaxies. That gives you their distance, and we compare that with the redshift, the speed of expansion. That gives us the Hubble constant. 2 other main methods are using what's called gravitational lensing, where a quasar, which is a very bright thing, is along the line of sight to a galaxy. And Einstein's general relativity says that the light from that background quasar can be bent along different paths around this galaxy, and that forms different images of the quasar. It's gravitational lensing. Quasars brighten and fade as the black hole accretes matter more or less. But these different paths have different time of flight because they're different lengths. If we measure the observed variations of these different images of the same quasar, and we measure the time delay, that sets the overall geometry of the system. It tells us the distances of the quasar and how much the paths deviate and stuff. And then knowing the redshift from a measurement of the spectrum and knowing the overall distance from this timescale argument, that also gives you the Hubble constant. Then there are other methods having to do with like type 1a's. There are other kinds of stars you can find, red giant stars, blah, blah, blah. But the other method, and I think this goes back to a question that you asked in a previous session where there just wasn't enough time to answer it, but I think you asked about masers. So a few galaxies that are sufficiently nearby have things called masers inside. They're like lasers, but with microwave radiation. You have a bunch of water molecules or hydroxyl, OH molecules, and they emit light at a very, very specific frequency, and we know what that is. But there are clouds of gas orbiting the black hole in the centers of these galaxies, and that orbital motion causes the wavelength of the emission to shift. From the amount of shift, that's a Doppler shift, we can tell how fast the clouds of gas are orbiting. Okay, that's a physical speed in kilometers per second. Using radio telescopes on different continents, very long baseline interferometry, we can actually measure the angular motion of those clouds of gas in the galactic nucleus. An angular motion together with a physical motion gives you a distance. It's like a little tiny distance is a big distance, sorry, a meter stick is a big distance times the angular size of that meter stick when you look at it in the sky. S equals d times theta. So similarly, if you take the derivative of that, then the speed of the motion is related to the angular speed. And that gives us then the distance. Knowing the distance and the redshift of the galaxy, again, gives us the Hubble constant. And all three of those methods agree pretty well. The best so far in terms of uncertainty is the type 1a supernova method, but the maser method is getting to be pretty good. Its primary shortfall is that there are not enough mazing galaxies, but the gravitational lens method, they've now found several systems, and they now get an error bar almost as small as ours with type 1As. And we all come in at 75 plus or minus a few kilometers per second per megaparsec. Okay, that was a great question, long answer, but I hope that answered it pretty well. You can find more on this online. Let's move on, Marianne, to the next question.
Okay, so our next question comes from a dad, and his name is Ed Guzman, and he sent the question in on behalf of his son, Sebastian, who's 10 years old. And he asks, since space is a vacuum, why doesn't the atmosphere from Earth just get sucked away? How can gaseous planets, suns, or anything exist in a vacuum?
Yeah, interesting question. I'm super glad, Sebastian, that as a 10-year-old, you're so interested in space. You know, much of life, at least here on Earth's surface, comes down to gravity, the pull caused by the matter in Earth, the pull on everything. That's why you don't go floating off into space. Our atmosphere is held to Earth by Earth's gravity. The sun is held together by Earth's gravity, even though it's really hot. It's a hot gas. It's millions of degrees on the inside, 10,000 or so degrees on the outside. You know, hot gases push outward. It would like to expand away, but it doesn't because gravity is stronger. And you know, a vacuum doesn't really suck. It may seem that way. You know, in the absence of a gravitating material, gas will just sort of fill any space. But that's just because gas expands. So it's not ever that a vacuum pulls. It's sort of an absence of pressure versus a pressure, and the pressure of a gas makes it expand into the vacuum. But if you have a strong enough gravitational field, a pull of gravity, like next to a planet or a star, then the planet holds in the atmosphere and the star holds in the gases that make up that star. Great question. Okay, next question.
All right, our next question comes from a regular viewer of ours, and she's a rather impressive 6-year-old.
Yay!
Her name is Sanvi, and her dad, Gorang, has sent the message in to us, and it's actually 3 parts. So I'll start the first one. One, can we see individual stars from another galaxy using powerful telescopes?
Okay, so the answer is yes, and that's something the Hubble Space Telescope is really good at, because being outside Earth's atmosphere, it has great clarity. There's none of the blurring effect, which is related to twinkling if you've got a telescope outside. And we can get rid of some of that twinkling using ground-based telescopes. Keck and Lick have excellent systems called adaptive optics. In fact, the adaptive optics with lasers was developed largely at Lick Observatory, seen in my background here. But now we use it a lot at Keck telescope too. But Hubble Space Telescope is great because over large angles in the sky, you get these very clear images. So you get a picture of a whole galaxy and you can see the brightest individual stars. And that's how we see the Cepheid variables with which we then determine the distances of type 1a supernovae. Okay, I think Sanvi had another question.
She did. So I'm going to skip to the third question because we've got a lot to get through. So her third question was, are there stars which don't have a galaxy?
Yeah, great question. Remember when I said that globular clusters can evaporate because especially when 3 or more stars come together by chance, one of those stars can gain a lot of energy and be flung out of the globular cluster? In a similar way, stars can be flung out of parts of the galaxy that are not the globular cluster. So there are what are called runaway stars or intergalactic stars that used to belong to a galaxy, but no longer belong to a galaxy. Good question. They're lonely stars.
So this next question comes from Bill Saylor of the Santa Cruz Astronomy Club. And he says, last time I heard Alex talk about the Drake equation, he was reporting very small numbers. Can Alex expand on why the number is now so low?
Yeah, Drake, so I'll give a brief answer to this one because I noticed it's 4:45 and I can go until 5, but I want to get through as many questions as possible. The question is, how many intelligent communicating beings out there are there in our galaxy or in our observable part of the universe? We don't know the answer to the question, and we'd like to know, and without searching, we will never know. So I want astronomers to keep on searching. There's a group called SETI, the Search for Extraterrestrial Intelligence, and I very much value what they're doing. My own reading of the odds is that, it's unlikely they will find anything. We might be the only ones in our own galaxy or one of a handful of intelligent communicating beings. Of course, our observable universe has 1 trillion galaxies, so I'm not saying we're the only ones in our galaxy. And I'm not even saying that we're the only ones necessarily in our galaxy, but there might be a handful. Unlike Carl Sagan, I don't think there are 100,000 or something. And very briefly, here are my arguments. First of all, we don't know how life arose on Earth, but even primitive life probably takes an extraordinary set of circumstances to form. Maybe so extraordinary that even primitive life is rare. But it did form 3.8 billion years ago on Earth. Okay, so then for most of those 3.8 billion years, it was single-celled. And only relatively recently did it become multicellular, maybe 1 billion years ago. And then 540 million years ago, it became hard-bodied and stuff like Cambrian explosion. Only 500 million years ago. And then evolution brought us, early hominids 4 or 5 million years ago. And then Homo sapiens about 250,000 years ago. And intelligence at our level then is just a brief blink of an eye of the existence of life on Earth. Over most of Earth's history, an intelligent alien would have said there's nothing particularly intelligent or mechanically able there on Earth. So it occurred only very recently and in a long and tortuous path that is not at all guaranteed elsewhere, at least not very frequently. And a path that didn't even necessarily lead to something that has a long-term evolutionary advantage. Now, there's no doubt that we improved the quality of life for hundreds of millions of people in the world in the last century, not without problematic things like climate change and particulate matter in China that kills 1.5 million people in a year. But I think, the Industrial Revolution has brought changes that were positive for most people. Just not clear that that's sustainable. And it's not clear that this kind of growth is to our evolutionary advantage. dinosaurs were around for 160 million years, and there's no evidence that they got any smarter with time. Cockroaches have been around for a long time. Our intelligence may be the thing that does us in. So there's been tens of billions of species of life on Earth. We have no evidence that anything has come anything close to our intelligence level or mechanical ability together. Dolphins and whales are pretty intelligent, but there's no indication that they can think abstract thoughts, have a curiosity, then go on to answer questions. And certainly they can't build machines with which to answer those questions. And then finally, there's the Fermi Paradox. If they're really that numerous, and you can imagine that if we were to continue our exponential growth in technology, we would reach a point where we could start populating the galaxy. And once you start that process, it's actually pretty easy to populate stars around many of the planets around many of the stars in our galaxy. And so if there were a bunch of such civilizations, and they could have started 1 billion years ago, right? The chemical evolution of our galaxy was sufficiently advanced 1 billion years ago that intelligent, mechanically able life could have originated. So if it's all over the place, why haven't at least some of those civilizations essentially populated the galaxy? That's the Fermi Paradox. I mean, other people asked it, but Enrico Fermi, a famous physicist that helped with the Manhattan atomic bomb project, said one day at lunch, where is everyone, basically? Why haven't we been visited in any obvious way? I don't personally find the claims of UFOs to exceed the high standards that we scientists demand of extraordinary claims. As Carl Sagan used to say, extraordinary claims require extraordinary evidence. And I don't think the UFO evidence is extraordinary. So I think we're rare. Microbial life, it's a different story. Probably more common, almost certainly more common than us. But even microbial life might be pretty rare. Okay, let's move on to the next question.
Okay, so this question is from Robert Marshall. He wanted me to first thank you for all that you provide and the love and for the universe and the exploration that you've been doing. And then he goes on to say, I heard it said by Neil deGrasse Tyson that hypothetically, if the sun were to blink out of existence, we wouldn't see it go dark for another 8 minutes roughly, but we would feel it immediately because the tug of gravity would disappear instantly with the sun. I understand the 8 minutes lag in light, and I understand the mechanics of Earth's orbit and the gravity of the sun, but I think it might be due to the fact that Neil deGrasse Tyson said instantly, while LIGO says speed of light, so folks don't want to get between them.
Okay, yeah, so I didn't hear what my friend actually, Neil deGrasse Tyson, said on this particular topic. One would need to go back to exactly the words he used. So let me explain it. Light would not be known, well, the sun would not fade out for 8 1/3 minutes, because that's how long it takes for light traveling at 150 million kilometers per second. I'm sorry, 186,000 miles per second, 150 million kilometers per second. I'm sorry, 150 million kilometers, the distance of the sun is traversed in 8.3 minutes. That's what I meant to say, at a speed of 300,000 kilometers per second, or 186,000 miles per second. So the light that the sun has emitted right now would still be on its way, and we wouldn't see the light from the sun blink out for 8.3 minutes. Gravitational waves travel at the speed of light, and I'm sure Neil Tyson knows this. So we wouldn't know by gravitational waves for 8.3 minutes either. I'm not sure that he said the word instantly. I mean, all of us do misspeaks. I'm sure he knows that gravitational waves travel at the speed of light. If he was deliberately making a distinction, if that was the whole point of the question or the remark, that, the light would go out instantly, the light would go out in 8.3 minutes, but we'd know gravitationally instantly, then, he's just wrong. But all of us have said wrong things occasionally. So we would know both of them in 8.3 minutes.
Okay. So this next question comes from Joe Perpage, I think that's how you say it. I'd like to ask Dr. Filippenko, since black holes are one of the most powerful, energetic question mark objects in the universe, why do we observe them in the lowest energy waves, radio waves? It's confusing and not really logical to me.
Okay. Interesting question. So I can think of two things that you might be referring to, and I'm sorry we can't have a back and forth here. In the interest of time, what we do is collect up all these questions and stuff. Quasars, quasi-stellar radio sources, were discovered in the 1960s, first with radio waves, quasi-stellar radio sources, and we now understand that they are supermassive black holes swallowing material. They are visible at X-ray and UV and infrared and optical wavelengths as well. It's just that when radio telescopes were developed for astronomy in the post-World War II years, suddenly astronomers started finding these bright points of light. And the sun is known to emit radio waves, but not profusely. So these profuse emitters were a little bit strange, right? But now we've seen them at other wavelengths as well, all right? But the radio waves come from electrons spiraling through magnetic fields very quickly. They produce a form of radiation known as synchrotron radiation, okay? But the optical and ultraviolet and X-rays can be produced by hot gas in an accretion disk around the black hole, okay? The other context recently is in the Event Horizon Telescope, where they used 8 radio telescopes all over the place to get that image of the black hole, the silhouette. And they used radio wavelengths because you can use this very long baseline interferometry technique really well at radio wavelengths. And that gives you extremely good clarity. The equation is that theta, the size of 2 stars or 2 objects that you can separate just barely, is lambda over d. And although the wavelengths of radio waves are big, and you might think that's bad because that makes theta big, the denominator d is the size of Earth, because there's a way to combine the signals from these radio telescopes, okay? And that gives you very, very super good clarity, clarity that we can't yet reach on Earth using, or even in space using telescopes. And again, the radio waves are produced by energetic particles spiraling around in magnetic fields. Okay, we can go to the next question.
All right, so, and this comes to something that we talked about at the beginning. This is a question from Arpit via Instagram, and he's asking, how can we best see Neowise Comet? What's the best location, time? Everything I read seems a little bit too obtuse for me to fully grasp.
Yeah. Okay, great question. I saw it this morning, folks. You can see the nucleus with the naked eye, if you know where to look. And you can even see the tail beautifully through binoculars. So the reason it's confusing is it depends on your latitude. It's in the northeast. And for the next few days at most US latitudes, and certainly here in California, the Bay Area, which I know is not where all of you live, but you can see it in the northeast about quarter to 5 in the morning, 4:30 to 4:45, then the sky starts washing out, okay? I saw it at 4:45 this morning, and the sky was already starting to get kind of washed out. Look to the northeast. Off to the southeast, you'll see bright Venus next to a bright star, Aldebaran. And then farther to the left, you'll see Capella, a bright star in the constellation Auriga. Then go down into the left from there and scan with binoculars, okay? But in the next week, certainly by this coming Saturday, it will have moved to the evening skies shortly after it gets dark in the northwest, okay? And for people in Canada and far enough north, the comet is passing sufficiently far to the north celestial pole that from Canada and maybe even the northernmost of the US, those regions are already nearly circumpolar, which means that they're above the horizon most of the night. I mean, you know, for, you know, yeah, for someone far enough north, you know, the thing sets in the evening and then rises in the morning, the very next morning. You can see it for both. But for most of us right now, it's still an early morning object around 4:45 in the morning. And then in about a week, it'll be like an hour after sunset, look to the northwest. But go to earthandsky.com or space.com or Google or whatever your favorite search engine is, comment Neowise location. I have a couple on my computer here. It shows the path. And many of you have these apps that show the constellations, and you can line them up with this map that you find. Some of them might even show the path of Neowise, and if you learn your constellations. But right now, it's to the lower left. It's to the northeast of Auriga. It's moving into Lynx. I'm looking at it right now. Right now, it's in Lynx. What is Lynx? Is that a lion? No, Leo is the lion. Lynx is, what is Lynx? Whatever it is. Then it moves into, looks like, then it moves into Ursa Major, yeah. But I'm looking at the path, all right? But look online, but northeast the next couple of mornings, and then starting Thursday, Friday, Saturday, northwest in the evening.
Okay. It's coming up to a couple of minutes to 5 now, so I'm going to make this the last question. I just want to say thank you all so much for all the great questions. And we will have Maurice back to answer the remainder of the questions, and no doubt more questions from you later on in the year. So because I'm all about encouraging young people, and I'm really impressed with the numbers of young people that are coming and watching these events, I'm going to make this last question from a young person who sent this in. So this is...
We'll keep all these questions for next time.
Absolutely, I promise. So this is from Rita, and this person is 14 years old and says that they are very interested in astronomy and astrophysics, especially about black holes. And so the question is, how do we know that black holes absorb all the matter around it? Because if it's very strong gravity, how does time contribute to this process? If so much mass and components are stacked inside the black hole that causes the black hole to get denser, how does this dense and small hole not explode? How does this affect time, and what might lie beyond a black hole?
Yeah, so that's actually a long, complicated question I wish to end. Let me just give a brief answer, and maybe I can give a more of an answer next time. So Rita, I'm glad that as a 14-year-old, you're so interested. So you're actually touching on a very interesting aspect of Einstein's general theory of relativity here. And the point is that the presence of matter warps the shape of space and actually the passage of time. And so if there's an observer who's going toward a black hole and you're far away observing that person, you will see their time slow down. You will see their clocks slow down. And they will age less than you. In fact, if they were to come back and let's say your twin went there, your twin, when your twin comes back, would be younger than you are. Your twin wouldn't be any younger than he or she was when they first started the journey, but they will be younger than you are when they return. And so time slows down. That concept was used in the movie Interstellar, in fact. 1 hour on the planet, Miller's planet, I think it was, orbiting the black hole Gargantua was like 7 years for people here on Earth, which is why the astronauts were trying to get back, because that one astronaut wanted to see his granddaughter before, you know, her life expired. So that's called time dilation. And in fact, right at the boundary of a black hole, time actually stops. And so you never actually see something cross the event horizon of a black hole. Regarding why the black hole doesn't explode, well, it's because gravity, again, holds it in so much that it can't explode. However, little tiny black holes that are evaporating through Hawking radiation, if such primordial black holes exist, will explode at the end of their lives, and they explode with a burst of gamma rays. Early in the study of gamma ray bursts, some astronomers thought they might be exploding black holes, but they're not. They don't have the right properties. So basically, it's through a quantum process that they can explode, but generally, classically, most black holes can't. And by the way, Marianne, I remember one question that I saw when a post on Facebook. It was from an old buddy of mine from high school, Karen Roth, now Karen Sheridan. And she asked, why does the tail of a comet always point away from the sun?
Yes.
I just want to mention it now because we were high school classmates, and also at UC Santa Barbara, we were undergraduates, and we took an introductory astronomy class. And one of the questions on the final exam was, why does the tail of a comet point away from the sun? And as a joke, Karen replied, I think she might have given the correct answer as well, but she said, because it doesn't want to get sunburned, okay? That's a joke. The tail of a comet, I don't know if Karen's on. Hi, Karen, it's been decades, but I remember that moment. So, no, the tail of a comet, I wanted to mention this, Comet Neowise in particular, points away from the sun because the dirty ice ball, or the icy dirt ball, evaporates as it gets close to the sun. And then the solar radiation, the particles and the light, push the material away from the comet, and thus in the direction opposite to the sun. And then the dust reflects sunlight and forms most of the visible tail. And that's why the tail points away from the sun. And Neowise has actually already passed the sun. It passed perihelion, as it's called. So it's on its way outward, and the tail is actually leading the head. So the tail is on its way outward. It's farther from the sun. You might think that the tail trails behind, and you might think that when it's on its way coming in, but no, that's not the reason. That the tail is being pushed away from by the radiation pressure. And you know that it can't just be left behind like hair, long hair. I haven't got a haircut for 4 months because of COVID-19, but if I were Fabio zipping through space, my hair would be flowing behind me. That's not what's happening. It's the radiation pressure from the sun. And right now, here's the sun, here's the comet, and the tail leads the comet as it's moving outward away from the sun. But the joke that Karen had was that it doesn't want to get sunburned. So thank you all. I'll let Marianne have the last words, but save your remaining questions. I actually think we got through most of them, but I'll have another session in August, okay?
Yes, and so even as we were talking, Alex, we had a number of questions come through on the chat, but also to our social at ucolic.org
Oh, great.
email.
If you could save all those then and type them up, Marianne, that'd be great.
I will do.
Wow, we had 130 and some odd participants. That's fantastic.
Yes, we had a great turnout.
And I hope I didn't go so fast. I wanted to cover questions, but also cover them thoroughly. So, if something I said didn't quite answer it, then just put some of the keywords in and look online, and space.com is a good site, for example.
And you can always rewatch this video back as well. It will go up on our YouTube channel,
great. Okay.
UC Observatories, and it's also available on our UCO Facebook page. So I want to say a big thank you to Alex for this hour that he's given us. I've got lots of nice comments come through on the chat thanking you for such an entertaining hour. So thank you so much, Alex. And
very good. And when it's possible, all of you come back up to Lick Observatory and visit us. We're so sorry that our summer visitors program had to be canceled this year, but it was in the interest of everyone's health, of course. Absolutely. Stay safe, everyone.
Okay, so I just want to tell you all that next week on Monday at 4 o'clock, we'll have a living room lecture, and that will be given to us by Dr. Shelley Wright. She's an associate professor in physics at UC San Diego. And her lecture will be about new ways to search for extraterrestrial intelligence. So that will be a really interesting one. So I hope you'll all join us next week at 4. And in the meantime, if you have any further questions, you can email me at social@ucolic.org. Thank you so much for joining us this evening. Goodbye, everybody.
Thank you. Goodbye.